like knock me out of like the course of like 30. Okay, hey, what's up, everybody? So we are getting back into it. We're talking about functions. We're talking about bijective, injective, surjective functions. It's going to be cool. It's going to be great. So section 5.2, we're revisiting the topic that we started this entire chapter with, which is how you can draw the arrows between the blobs, right? So injective, surjective, and bijective functions. That's what this is all about. People also occasionally, well, bijective will usually still stick around, but people occasionally also call these one-to-one, onto, and potentially maybe people also say invertible functions. The notational convention here of saying injective, surjective, and bijective is actually not as old as you would think, but it's the one we'll stick with here. So you may see other ones. Like many things in math, there are multiple names people like to call the same things, and for some reason, people can't agree on it, right? There's no international council of mathematicians who decide on the names of things. Though if there was, I would love to serve on that committee and have a lot of fun with it. So, definition. Let's just hit it up straight up with the definition, then we'll draw some pictures. We'll think about what all this says. So, a function f from a set x to a set y, which I will write with bars to make it clear that they are the capital letters, is said to be, here are the three possibilities. 1, injective, if for all x and y in x, f of x equals f of y implies that x equals y. We'll draw pictures to make this all super clear very soon. Surjective, if for all y in y, there exists x in x such that, I won't abbreviate such that, I'll just write it out all the way, such that f of x equals y. Okay, and finally, 3, bijective, if it is both injective and surjective, both of the jectives, as you might say. Bijective, two jectives. What's ejective? I don't know. But hey, there you go. Okay, let's think about what all this is saying. Let's draw the picture. So here's the idea of it all. And I will start by drawing, I'll draw the picture over here to start with. And then we'll summarize over there. So here's the gist. You got your set x. You got your set y. Now, you got some stuff over here. I'll write, like, say, like A, B, and C. And then over here, I'll write some numbers. How about like 1, 2, and 3, maybe something like that. Okay, cool. Here's the idea of, even better for, I'll start with a slightly bigger set to make some of these things distinct. So for injective, what it says is that for all pairs x and y and x, having the same value means that they were the same thing. Or putting it another way, the only time that you get f of x equal to f of y is if x is equal to y. What does this say in terms of arrows? It means that if something gets pointed at by your function, nothing else points at it. That is, this case right here, not injective. You already know it. All you have to do is look at the stuff over in this y column, the codomain, and say, hey, does anything have 2 arrows pointing at it? If anything has 2 arrows pointing at it, not injective. If anything has 3 arrows pointing at it, not injective. since having 3 arrows pointing at it means you also have 2 arrows pointing at it, right? Okay, so injectivity is just, hey, is there anything that gets pointed at more than once? Now, something like this, injective, yeah? Everything that has an arrow pointing at it has only one arrow pointing at it. Not everything has an arrow pointing at it, but everything that does has only one. Yeah? Injective. Feel all right? I think when you write the definition, it seems kind of weird at first, right? F of x equals f of y implies x equals y. What the heck? What kind of implication is this? All it's saying is that the only time, or that you don't have different things that have the same values. That is, if you have same values, same thing. Yeah? Get the same thing out, you must have put the same thing in. Okay. Now, surjective, on the other hand, is more the other part of it. So maybe that doesn't sound too sensible, but here's kind of what I'm saying. Is here we said, okay, does everything have just one arrow pointing at it, or not more than one? Surjective says, does everything have at least one? And that's the only big difference. So here, if I do the exact same thing, it would be not surjective because 2 doesn't have an arrow pointing at it, yeah? Well, on the other hand, something like this, definitely surjective because everything over here has an arrow pointing at it. Okay. And indeed, if I threw a D in there and I pointed that one at 3, still surjective. Everything has at least one arrow pointing at it. It could have more than one. Surjective means at least one. So here's the idea. Injective, not more than one arrow pointing at anything in the codomain. Surjective, not less than one arrow pointing at anything in the codomain. And then, of course, if you have not more and not less, bijective, not more than one and not less than one. How many do you have? Exactly one. Okay, cool. Do you see how they're kind of dual? Even though their definitions look wildly different, right? Injective is like, hey, you have this implication is true. Surjective is like existentially quantified predicate. In fact, it's even more complicated than that. If you want to write like the predicate you would have to have. So here, what's like the predicate for injective? So for all x, for all y, and I should maybe be clear here. For all x and all y in x, f of x equals f of y implies x equals y. That's the predicate for injective, this guy right here. And here's the quantifiers that turn it into a proposition. Yeah? Okay, what about for surjective? There exists an x and x such that f of x equals y. So there's the predicate, f of x equals y. Here's the quantification. They look different. it doesn't look like you've just flipped one thing. But if you write it in terms of arrows, it becomes very clear that they are just like flip one thing, right? Like just flipping more than to less than. Like that's the only difference if you think of it in terms of arrows. And that's why I think that thinking of injective and surjective functions in terms of arrows between blobs, while largely kind of like a heuristic tool to help us see what's going on intuitively, is basically the right way to think of it in your head. That is, these are like the formal ways of writing it. But the picture you should have in your head of what these things mean is arrows between blobs. And the simple statements that injective means not more than one arrow pointing at anything in the codomain. Surjective means not less than one. Then it makes it super clear that bijective is one and exactly one arrow pointing at each thing. OK, cool. So injective, surjective, bijective. How are you feeling about it? OK? All right. Now, when we first encountered injective, surjective, and bijective functions, when we first started talking about all this stuff, drawing blobs, I made a claim to you that there is a nice property of injective and surjective functions, namely that we all know bijective functions are invertible. That's like kind of how you've been classically presented the idea of bijective, or like in algebra classes, you've probably seen some notion of like, when is a function invertible? Well, the answer is that everything in the codomain has to get hit by something, and it has to get hit by only one thing. Otherwise, how would you pick which one, right, to have for your inverse function? OK, you've seen that. But I think that it's nice to look at surjective and injective functions as the left and right invertible functions. So you can see that a bijective function is a function that has both a left and a right inverse. So we'll get back to this. We'll prove this more formally. But just from the way we draw things with arrows, I think it kind of makes it clear that what's going on is closely related to whether or not you can flip the arrows and get a function, or if you can make another set of arrows to get back to where you started. So we'll talk about that more. We'll redraw these pictures. We'll see it all again. But first off, let's do a couple of examples with functions we talked about last time, just to remember them, and also just to get a little bit used to this. So last time, we talked about a couple of specific types of named functions you'll see quite frequently. So let's consider the functions from example 5.4. So first off, let's talk about for a non-empty set A, the identity function I from A to A, i.e. the function I of A is equal to A for all A in big A, is both injective and surjective, right? Do you agree with this? Yeah? OK, it is both injective and surjective. To see this, let's say, suppose I of A equals I of B. Then, since I of A equals A and I of B equals B, certainly A equals B. So I is injective. Yeah? Just from the definition, right? What the identity function does is it sends an element to itself. So if I of A is equal to I of B, then A is equal to B. That's exactly the thing we need for injective, right? So that implication is satisfied, hence injective. What about surjective? For surjectivity, then I of B is equal to B, or I'll say it this way, then I of A is equal to B for A equals B. Hence, I is surjective. That is, you can pick anything in the codomain, and no matter what thing you pick, there's always something in the domain that you can send through the function to get to that thing. That thing is the same element that you picked from the codomain, because the domain and the codomain are the same. Does that make sense? Sweet, okay. So we've got the identity function, injective and surjective. Did anyone say not make sense or feeling weird about it? What do we think? Okay, some people may be feeling weird about it. All right, so what do we need for surjectivity? For all y and y, that is in the codomain, there must be at least one thing in the domain, some x, such that f of x is equal to that chosen element from the codomain. So to show something is surjective, pick an arbitrary element of the codomain, and then reverse engineer an input such that f sends that input to your arbitrarily chosen element. It's not the case that the input has to be arbitrary. The input will depend on what your codomain element is, right? But you should be able to write effectively like some type of a formula, right? In the sense that, or somehow show that such a thing exists. In the sense that whatever y you pick, then for that specific y, whatever it happens to be, some x can be chosen, which can indeed depend on y, such that f sends that thing to y. In this case, it maybe seems strange because of how straightforward it is, right? The thing that hits any chosen element is the exact same element, right? The identity sends an element to itself, so it certainly hits every element. It hits it with the input that is the exact same as the desired output. Yeah? Injectivity, on the other hand, says that if you get the same output, you must have had the same input. Now, for the identity, having the same output, well, we know what the output is. It's the same as the input. So we automatically get that the inputs were the same, right? Maybe perhaps the identity function is so straightforward of an example that it actually somehow seems weirder or harder to deal with, right? So let's try another one. Okay, what about a constant function? Okay. Oh, let me number this. Let A and B be non-empty sets. Let I'll even say this. Let K from A to B be a constant function, i.e., there is some B in B such that K of A is equal to B for all A in A. Yeah? A constant function sends every single thing in the domain to the exact same element in the codomain. It is constant in the sense that its outputs don't vary. They don't change. They just stay the same. Nice, dependable outputs. It's always the same dang thing, right? Okay, constant functions. Injective. We should be careful, perhaps. Then, K is not injective unless A has only one element. Since if A has only one thing, well, there's no possible way to fail surjectivity. Injectivity, sorry. Injectivity says, hey, if you get the same thing out, then you must have had the same thing you put in, right? If there's only one choice for what you can put in, there's no way you can get the same thing out from two different things. There's only one thing to have in the first place, right? So every function from a one-element set, constant or otherwise, is injective, right? So, okay, so if A has only one element, then a constant function can be injective. But in any other situation, it won't be. Actually, I'll make that a parenthetical remark, unless A has only one element, since K of A equals K of B for all A and B in A. That is, for every single element, you get the same output, right? And as long as you have more than one element in your domain, there is one case where you have two different things. There's at least one case where you have two different things that give you the same output. Everything gives you the same output, right? What do you think? Does that make some sense? Okay. Draw the picture of it if you're feeling weird about it. Here's the picture of it. You got A, you got B. There could be a whole bunch of stuff in B. Who knows what's in B? But there's some specific one that everything in A gets pointed to, right? Now, if there's only one thing in A, then the whole function is just one dang arrow. But if there's more than one thing, then every single thing points at that one very special element, and that's what your constant function looks like. So certainly not injective. Now, what about surjective? Well, what if B has just one element? Then it's surjective. Okay, what if B has two elements? What if B has three? No. Okay, so kind of the same as before. There's only one sort of pathological case. It's when B is very small. So, likewise, K is not surjective unless B has only one element. Since since the only element of B for which there exists any A in A satisfying f of A equals B, I should say B of B, is the value I'll say just there is the constant value of the mapping. That's perhaps the cleaner way to say it. That is, there's only one thing you get out. So if the B has more than one thing in it, then there's something you don't get, right? Yet again, the picture. All the arrows pointing to a single dot. If there's more than one possibility, then there's some dot that has no arrows pointing at it. Yeah? Okay. Identity functions, constant functions. Feeling all right about these two? Well, let's try some more then. What other ones could we have? What about, for instance, what was the next one that we did? Oh yeah, the projections. Yeah. Okay. Let A and B be non-empty sets and consider the projections pi a from A cross B to A and pi b from A cross B to B, i.e. pi a of an ordered pair AB is equal to A, and pi b of an ordered pair AB is equal to B for all ordered pairs AB in A cross B. That's what those guys are, if you've forgotten. The projections are just, hey, you got an ordered pair, what if you only look at one of the things, right? It's like a natural kind of obvious map. Just you got an ordered pair, cover up an element, right? Which one do you cover up? You got two choices. So you get two projections. Are these guys injective, surjective, what have you? Let's think about it. We can draw a picture even if you'd like. Here's the picture. Remember, what does a product look like? If you want to think of a product looks kind of like this. You got a set A, you got a set B. And then if you want to build the product, here's what you do. For every A in A and every B in B, you trace on over and trace on up, and you get a new element. You trace on over and you trace on up and you get a new element. I'm, of course, relying on our physical kind of geometric intuition to say, like, look, you're, getting a new element for each thing, right? In the set. I should have drawn fewer dots. Now this feels like it will take forever to write out. But, you get the picture, and so on, right? Basically, it's like you take one from each one, right? And then you end up with a product, A cross B. Of course, A and B have no intrinsic ordering to them, so drawing it in this nice grid-like way, I guess, would require some sort of like an entirely arbitrary choice of how you happen to line up the things in A and the things in B, right? But borrowing from your intuition about, like, graph paper, right? It's the same idea, except unlike the numbers on like a regular old number line, which do have a nice ordering to them, these don't necessarily have any ordering to them at all. But if you just put them in a random order, then hey, there you go. Now you got an ordering, and now you can make this grid. All right, so it's a grid of dots. What are the coordinate projections? They're basically just these like lines right here, right? That is, if this is A cross B, here's pi A. It takes everything from here, and now assuming I've written all my stuff in the same way, every single one of these guys in this whole line, every single one of them gets mapped to the same exact thing. Every single one of these guys gets mapped to the same exact thing. Well, we should be a little bit careful. Notice there are exactly as many copies as there are elements of B. What if B has only one element? Then I've basically just rewritten A, right? Oh, so it could be it could be injective if B has only one element, right? That is, the projection pi A could be injective if B has only one element. What about surjective? Well, what thing is not going to get hit? Is there anything in A that doesn't get hit? Yeah, indeed. There's always, for every A and A, pick any element of B, right? Then that A and whatever B you choose gets mapped to that A by the projection, yeah? So, surjective, yes. Okay, so let's write out what we've got here kind of from our picture. Maybe that picture was sort of a hellish mess of arrows, but maybe it makes it clear. Then, pi A is not injective unless B has only one element. Since AB1, I'll say it this way, pi A of AB1 is equal to A, and pi A of AB2 is equal to A for any A in A and B1, B2 in B with B1 not equal to B2. That is, there has to be some B1 not equal to B2. That is, B must have at least two elements, right, for this trick to work that shows it's not injective. Agree or no? That is, when we drew that picture, every row got sent to the same thing. Each row, every element in a row got sent to the same thing. Okay, so the only case where everything in the codomain has only one arrow pointing at it is when every row has only one thing in it. And the number of things in each row is the number of things in B. So the only case where you would have injectivity is when B has only one thing. Okay. What about surjectivity? Yeah. However, it is always surjective, since for any A and A, we may choose whatever B and B we desire and get pi A of AB equals A. This works even if B has only one element. The only time you wouldn't be able to do this is if B is the empty set. Yeah? Okay. So, and a fun exercise. What happens in a product when one of the elements or one of the sets is the empty set? Let's just write it out really quick. Think about this really fast. A quick little exercise. Okay, so A cross B is defined to be the set of ordered pairs AB such that A is in A and B is in B. So if we replace B with the empty set, is there any ordered pair AB that would satisfy the predicate defining the set? There's nothing in the empty set, right? So Cartesian product with the empty set, under the conventions we've done here, is itself the empty set, which is kind of nice. It means the empty set sort of acts like a 0, right? Multiply it with anything with 0, you get 0, right? Hey, cool. Fun little side note. Okay. So, fair enough. What about pi b? Does it kind of work the same way? What about the projection onto the second coordinate? Is it injective? No, unless A has only one thing. Is it surjective? Yes, because A has at least one thing. Yeah. Right on. And it's for basically exactly the same reasons. Okay. So the same exact answer, except switch your A's with B's and your B's with A's. And then you're good to go. Okay. What about characteristic functions? Let's try those guys. Let's see if we can figure it out for characteristic functions. let A be a subset of the reals and consider the characteristic function of A, i.e. the function chi A from R to, well, you can say from R to R, or if we want to be a little bit pithy, we can remind ourselves and say it's really from R to 0, 1 or something like that. Notice those actually aren't the same function. They have different codomains. So it's essentially like a matter of convention, whether you define it this way or you define it in the other way. I personally have always preferred to see it as going from R to R, because then it makes it easy to write functions without having to first do an embedding of the result of the characteristic function. But if you prefer it the other way, that's totally fine too. You'll just be implicitly probably neglecting to write some embeddings. Okay. The characteristic function chi A from R to 0, 1 defined by chi A of x is equal to, well, 1 if x is in A, and 0 if x is not in A. That's the definition of the characteristic function. Okay. Then, chi A is injective or is not injective? What do you think? Then it would be, okay, let's think about it really quick. If A has one element, is it injective? Well, there's only one time 1 gets hit. What about 0? It doesn't get hit? There sure are a lot of things in the reals like other than just that one element, right? Okay. Yeah, would we have it be injective? No. Let's think about it. Is it ever injective? Could you come up with any sort of like a crazy set where it would be injective? R. If A is equal to R, okay, then everything would get hit by, everything would be, have the value 1. It would be the constant function 1. Is a constant function ever injective when the domain has more than one element? No. Yeah, you'll either have a lot of 1s or a lot of 0s, or both a lot of 1s and a lot of 0s, right? There's a lot of dang real numbers. Quite a lot. We'll talk about that more later. But yeah, it's not injective. To write the justification of what we just said is that since we either have, I'll write it as some cases. 1, A is equal to R, and chi A of x is equal to what? 1 for all x in R. 2, A is equal to the empty set, and chi A of x is equal to 0 for all x in the reals. Or 3, A is not the empty set, nor is it all of the reals, and there exist at least 2 values x, y in R such that chi A of x equals chi A of y, and x is not equal to y. If I wanted to say this more formally, I suppose, I should say, well, if A is not the empty set and it's not everything, then I could break it into some cases, and I could say A either has at least 2 elements, in which case, hey, there's 2 different things. Pick 2 things in A. Those things both get mapped to 1, not injective. Or if A has only 1 element, then there are at least 2 things outside of A. Yeah? So you can break it down into those 2 cases. A has at least 2 elements, or A has only 1 element. And then you could show in either case you get non-injectivity. But to keep it, I guess, pithy, I suppose you can see what's going on well enough without that. Does that feel sensible or no? Maybe? Okay. Seeing some like, which is one of those. Okay. Basically, I can put it in parentheses, i.e., if A has 1 element, then pick x not equal to y both not in A, and if A, or if I'll say it this way, if A has more than 1, pick x not equal to y with both in A. Yeah? Does that make sense? If A has only 1 element, then you could pick the 2 things to be outside of A. That's certainly possible, right? There's more than 1 real number. There's more than 3, which is what we need, yeah? And if A has at least 2 elements, then just pick both of them to be an A and you're done. Either way it works. Okay. What about surjective? We have cases as well. So chi-A is surjective unless A is equal to the empty set or A is equal to all of the reals. For this reason above, the fact that you get a constant function otherwise. Yeah? Sorry, I'm getting low on the board there. That might be putting the monitor in the way for some of you. Reasonable? Okay. So I won't write really small on the board up there, since we already gave the justification above, showing that it's a constant function in each of those cases. All right, injectivity, surjectivity. Boy, that's a lot of examples. Fun. Next time up, we'll talk about compositions of functions. I won't write anything on the board since we're down to the last 2 minutes, but compositions of functions, the nice way we all know and love, which just is all about following arrows. Naturally, the blobs have to line up if you want to think of it that way. So compositions, not so bad. Basically the whole picture of it, which we will talk about in great detail next time after a nice, good weekend. It just says, hey, you got a blob A, you got a blob B, you got a blob C, you got some arrows from A to B, and you got some arrows from B to C. Then you can get some arrows from A to C just by following the arrows across. That is, you can just go whoop, and there you go. Now you have an arrow from A to C, right? That is, you can take a function f from A to B and a function g from B to C, and you can take and finish this sort of diagram right here by saying, hey, look, first I can do f, then I can do g. Unfortunately, our notation tends to write this in kind of the backwards order because we plug things in on the right to functions, yeah? Okay, cool. So other than this unfortunate mismatch, and some people think we should write like x of f instead of f of x just to get rid of this problem. It's pretty straightforward, and you've seen this before. So we'll have fun talking about it. We'll get back to left and right invertibility and genuine two-sided invertibility, and it'll be great. I'll see you around. Have a good day.